Hi class, so in this video I'm going to talk to you about how to draw a Lewis structure. A Lewis structure is a two-dimensional image of a molecule, and to restate, a molecule contains covalent bonds. In the previous video, chemical bonding and electronegativity, I also talked about ionic bonds, but in this case we're only drawing structures that have covalent bonds in them. So you should have this handout next to you as you take notes and follow along. I'm not going to read these steps to you. I'm going to read them as I do them in the examples that I'm about to show. It's important to know what a duet and an octet are first, so let me go over that. A duet, as you know, is a song that is sung by two people, and an octet, and the prefix oct, refers to 8. In all the electron dust structures that you drew in the previous section in class, you notice that the maximum number you could have for the valence electrons was 8. So for neon, you drew 8 dots around, and same with argon, and same with krypton, and so on for the noble gases. This maximum number that every atom on the periodic table is trying to get to is 8 valence electrons. That's referred to as the octet rule. Now there's two exceptions to that, and those fit the duet rule. That's hydrogen and helium. You notice that on the periodic table, the first row, the first period, has only 2 elements in it. The first shell can only fit 2 electrons. And just to prove that to you, when you look at your periodic table here, you notice that this first row has 2, but every other row, if you exclude the transition elements and the inner transition elements, every row has 8, right? 2 on this side and 6 on the right side. This is how you get this shape of the periodic table, with 8 in every row if you don't include the transition elements. So let's do some examples. So the easiest example to do is F2. So the first step, as shown on this list here on how to draw a Lewis structure, is count the valence electrons in the formula. So the example was F, and you see that F is in group 7A. So it has 7 valence electrons. So you take 7, and because there's 2 fluorines, you multiply by 2, and you get 14. So the next step in the procedure says, draw a skeletal structure with the least electronegative atom in the center. Now with 2 atoms, there is no center atom. So we're just going to draw 2 F's next to each other, and a line representing a bond, 2 electrons between each outer atom and the central atom. So we're going to draw a line, and now that's 2, right? 2 dots is the same as a line, but we draw a line in between 2 atoms. We have 2 electrons so far, right here, but we want to get to 14. How do you do that? Well, it says here, add electrons to each surrounding atom until it has a complete outer shell, a duet or an octet. And since F is not hydrogen or helium, you're going to fill in those dots. So it's 1, 2, 3, 4, 5, 6, and now this F has 8 electrons because you count all the ones around there, and there's 2 here, 2, 2, and 2, and that makes 8. Now we do the same thing on this side. And you see that around this fluorine, there's 2 for the bond and 6 other lone pair electrons, and that adds up to 8 as well. So they both meet the octet rule. But now we want to check it to make sure that it's actually 14 total. So let's count them. 2, 4, 6, 8, 10, 12, 14. And we're done, because the number of electrons in the structure matches the number of valence electrons that we counted. In this first example, we used the first 3 rules. Our next example is CH4. And carbon, from our periodic table, is in group 4A, so it has 4 valence electrons. And hydrogen, which is in group 1A, has only 1 valence electron. We're going to do that math now. 4, and there's only 1 carbon, and there's 1 hydrogen times 4, which means that our answer is 8. So we're trying to get a structure of 8. So it's important to note at this point about atoms with only 1 unpaired electron on the outside, like hydrogen or like fluorine. They can only bond once, and they're always on the outside of molecules. So the carbon has to be on the inside, with the hydrogens on the outside. Okay? You go to the second rule, draw a skeletal structure with the least electronegative atom in the center and a line representing a bond, 2 electrons, between each outer atom and the central atom. So we're going to draw our line, 1, 2, 3, 4, which represents 8 electrons because each of these lines is 2 electrons, and that actually gets us our answer. So we should be done. But let's check our rules again. Step number 3, add electrons to each surrounding atom until it has a complete outer shell, a duet, or an octet. So that has to be true in order for us to be done. So we check each atom. There's 2 electrons around that one, 2 electrons around that one, 2 electrons around that one, and 2 electrons around that one. Since it's hydrogen, it has to meet the duet rule. Each one of these meets the duet rule. And then we check the atom in the center, and we notice that there's 8 electrons around that one. And that one then meets the octet rule. And that's done too. So that's the correct answer for CH4. So in that example, we used, again, only steps 1, 2, and 3. So now we're going to go to our next example, which is BeF2. So Be is in group 2, so it has 2 electrons, and F is in group 7A, so it has 7 valence electrons. So we do 2 plus 7 times 2. 7 times 2 is 14. 14 plus 2 is 16. When you look at the rules here, you'll see in these comments that B and Be are electron deficient. They will always have less than 8 valence electrons in a correct Lewis structure. So we have to make sure we keep that in mind when we do these problems. Now, Be is going to fit in the center. You'll get a good intuition about this, but F's can only go on the outside of atoms as well. So we draw our bonds connecting, and that's only 4 electrons so far. As it says in step 3, we add electrons to complete the octet. So we're going to do that. So now that fluorine around here has 8 valence electrons, and that completes that octet as well. If you count 8 over here and 8 over here, that gets us to 16. And there's no other valence electrons here or here because Be never fills its octet rule, as stated by this second comment. In that example, we used the first 3 steps plus the comment, the second comment, on this procedure to draw Lewis structures. So our next one is NH4. This is a different problem because it has a plus there. And a plus means that it has lost electrons. So we have to include that in the math when we calculate the number of valence electrons. Nitrogen is in group 5A and hydrogen is in group 1A. So nitrogen has 5 valence electrons, hydrogen, which is 1 valence electron, times 4 because there's 4 of them. Now because NH4 has a +1 charge, you're going to subtract 1. If it's positive, it's lost electrons. If it's negative, you would add the electrons. So this is 5 plus 4 minus 1, which is 8. We put nitrogen in the center because hydrogen never goes in the center. It can only bond once. We draw the bond connecting the atoms together. And there, notice is 2, 2, 2, 2. And that's 8, which matches that number that we counted in the beginning. Hydrogen, remember, fits only the duet rule. And you notice that every hydrogen around here meets the duet rule. And we notice that nitrogen meets the octet rule right there. So that's good as well. Now, with this structure, which I'm going to redraw over on this side, because it's positive, you have to indicate that in your completed structure. So we put brackets around it, and we write up the charge on the outside. So it's NH4+. So in that example, we used the first 3 steps, but we also made sure that we understood when we counted the valence electrons that if it's plus, you have to subtract the electrons, and if it's negative, you have to add electrons when you calculate the total number of valence electrons. Okay, in the next example, we have O2, oxygen, and we notice that oxygen is in group 6A, so it has 6 valence electrons. 6 times 2 is 12. We draw our O's next to each other, with a line in between, and that's 2 electrons. We put our lone pair electrons around the outside to get to 8. Notice that there's 8 surrounding both atoms. But if you count it, 2, 4, 6, 8, 10, 12, we have 14. We have too many electrons. So what do we do? Well, let's go to our rules. And we see here, if you've exceeded the number of electrons, make extra bonds by bringing in lone pair electrons from the surrounding atoms. So that's what we're going to do. So what you do is you circle 2 lone pair electrons surrounding the bond, and you bring them in. And when you bring them in, it takes 4 electrons and makes them 2. This is just a shortcut to help us as humans understand what nature is doing with those electrons. So we're taking 4 electrons, making them 2, so it's reducing the structure by 2 electrons. Let's count again. 2, 4, 6, 8. Remember, each line is 2 electrons, 10 and then 12. So that matches that, and so that's our correct answer for oxygen. So in that example, we used 1, 2, 3, and step number 5. So in the last example, which mimics kind of the hardest problems that you'll ever do, we have SF4. So S has 6 valence electrons and F has 7. So we do 6 plus 7 times 4 equals, so 7 times 4 is 28. 28 plus 6 is 34. So we put S in the middle, put F around it, and we notice that gives us 8. Well, we need to fill in the octet. And notice there's 8 around every one, so it's 8 happens 4 times, so that's 32. But we're 2 short. What do we do? Well, let's look at our rules. If you have remaining electrons, you can add them to the central atom, but that's only true if they are in the 3rd period or above. And notice that sulfur is in the 3rd period, because these heavier atoms have these d orbitals, which we're not going to cover in this video. This is the reason why they can break the octet rule. So we put this lone pair of electrons, and I know I said previously you can't put them on the corners. That's really the only place you can put them in a 2-dimensional image. So you can put them on any corner, because it has 34 now is how to do it. So please write down questions and I'll be able to answer them in class. Thanks.